Greetings everyone, Dr. Carroll here, Chem 1111. This is lecture 2 in unit 5. First lecture was a big one, learning all about electron configurations, and in this lecture we're going to apply those configurations and those ideas, effective nuclear charge, size of orbitals, to properties that repeat themselves. Our big focus is on main groups, which we now know from the periodic table, group 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. We can look a little bit at the transition metals, but the properties work best when you focus on the main groups. And the properties we look at based on this slide here, so this is slide 39 in your PowerPoint collection, is atomic radii, which is given the symbol R, ionization energy, in particular I1, so the first ionization energy, and electron affinity to a lesser extent. So one explanation that helps understand things is as the principal quantum number increases, things get more energetic, and the atomic orbitals, things meaning the electrons, become more energetic, and the atomic orbitals become larger and less stable. So as n increases, the effective nuclear charge is going to increase slowly, and it increases because there are more protons, right? As z increases, any given orbital becomes smaller and more stable. So you have this bit of a battle between the two of them. So going down a group, orbitals expand, the stability decreases, and going across for a given shell, the orbitals shrink and the stability increases. So, they want to go to atomic radius already on the slides. That seems like a bit of a jump. Let's go to our mini text here, and we've already said that. Here I'm in the mini text section 5.4. Okay, across here, they're talking about atomic radii, the size of an atom. As you go across a row, the atoms get smaller. As you go down a group, the atoms get larger. The atoms get smaller as you go across a row because the effective nuclear charge increases. You don't have that screening, inner shell screening of electrons, because your valence electrons are all still in the same valence shell. Okay, so let's jump straight into atomic radii in the textbook. Atomic radii is given by the letter R. Most of the volume of an atom is occupied by its electron cloud. The size of an atom is determined by the size of the orbitals. Now I could look at size in terms of a volume. If I take the average electron density as being a sphere, then I could talk about an atomic volume as 4/3 pi r cubed. And way back, would you believe, 1987, 2000, 33 years ago at least, I wrote a paper with a bunch of other guys way smarter than me about atomic volumes. But we don't have to use atomic volumes here. We can just look at the radii because the volume is proportional to radius cubed, so fine. Radius goes up, volume goes up as the cube of the radius. So going across a row, the atoms get smaller from left to right and increase from top to bottom, and they get larger as you go across. So figure 515, where's that figure? Here it is. So if I look here at my second row, there's helium. Well, that's the end of the first row. Okay, here we go. Here's hydrogen, then helium. So as you go across, the atom gets smaller, right? Here's my second row. Lithium has a larger atomic radius, PM's picometers. And so we're just plotting against the atomic number. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So neon is the smallest atom as you go across the second row. Most of you will remember reviewing this from last year. If not, well, you're seeing it now. If you want extra practice, there's always Khan Academy, and Brightstorm is good on atomic radii. I like the Brightstorm videos as well. Third row, And of course, there's our friend Tyler DeWitt. Sodium, I don't know if he's my friend really. Sodium is largest in the third row and decreases as you go across. So you see how the trend repeats itself. The atoms get smaller as you go across each row. From potassium to krypton, they get smaller. From rubidium to xenon, they get smaller. From cesium to radon, they get smaller. Now, when you start to do the fourth row, there's little glitches happening with the D blocks and the F blocks. So those are finer features that we aren't really going to make a big deal about. I'm going to focus mostly, like I said, on the main groups, on the brain groups, on the main groups. Now, what about in a given group? For example, in the alkali metals, here's lithium, sodium, potassium, rubidium, cesium. You see that as the atomic number goes up, in a given group, the size goes up. Okay, and you're going to say, oh, but there's more protons, it should shrink. But then, as you read before, and we've talked about, the intervening filled or partially filled inner shells are going to help decrease the value of the effective nuclear charge. Thereby, the atoms are larger. So, as you go down any main group, the atom at the bottom of the main group is larger than the atom at the top. So the largest atom of them all is francium, right? And the smallest atom of them all is helium. Here, that was the alkaline metals. How about the alkaline earth metals? Well, yeah, it would be like this, right? And then the boron family. So you see, they all get the increases. Yeah, I know there's other stuff happening, weirder stuff, when you get to other parts in the D blocks. Here we have the noble gases, so they increase as you go down from helium to radon. What increases? The atomic radii. Okay, so let's do example 5.8 here, and I should probably get my practice exercises set here. As you're staring at that question, okay, which atom is larger and why? So I got my periodic table right beside me, and you don't have to memorize the periodic table. Silicon or chlorine? Well, chlorine is going to be smaller because both silicon and chlorine are in the same row, so silicon is going to be larger. Okay, a whole long story. Chlorine is smaller, silicon is larger. Sulfur is selenium, selenium gomesium, selenium dionium. Selenium is lower down in the chalcogen group, so it is going to be larger. There's all those intervening atoms, and you can read that explanation. Molybdenum or silver. Okay, now this is in our transition metals. We aren't going to do many of those, but as you go across a transition metal, if it's in the same row, here it's row 5, they are going to get smaller. So molybdenum should be greater than silver. Let's see if that's true. These offset molybdenum and silver are nearly the same size. I thought molybdenum would be a bit greater based on this discussion. In each case, you have a 5s, and then you get the 4d. So molybdenum is 4d5, silver is 4d10. 4d is effective, has screening, has 5s roughly. Nuclear charge of silver is 5 more, so that should make it smaller, but does have 5 more screening electrons, so they're nearly the same size. I wouldn't ask you this question. This is too much of a borderline question, but they're roughly the same size. Fine. But again, transition metals aren't our big focus in the trends here. Which is smaller and which is larger than arsenic? Okay, so arsenic. So I'm going to have phosphorus. So phosphorus is going to be smaller because it's just above it, smaller. Then we have germanium. Germanium is to the left of arsenic, so it's going to be bigger. Selenium is to the right of arsenic, so it's going to be smaller. Antimony is lower than arsenic, so it's going to be larger or bigger. Okay? So that's atomic radii. Now I'm just looking to see if the book talks about sizes of ions. Yeah, the ionic radii we'll get to just a little later. So that's atomic radii. Now ionization energy. We looked a bit about this when we looked at our energy level diagram for a hydrogen atom. First ionization energy increases from left to right across a row and decreases from top to bottom. When an atom absorbs a photon, the gain in energy promotes an electron to a less stable orbital. As electrons move into less stable orbitals, they have less electrical attraction. If the absorbed photon has enough energy, an electron can be ejected, as occurs in photoelectron spectroscopy. So that's one way to ionize an atom. And the minimum amount of energy needed to remove an electron from a neutral gas atom is called the first ionization energy. This book uses IE1. Other books just use an italicized I1. I like to use just the I1. And they roughly mirror the trends in the radii. So as I go across a row, the first ionization energy increases. Now, what's interesting is it doesn't increase smoothly. It increases in the group number. First group 1, I'm just talking about main groups. Group 1, then group 3, then group 2, then group 4, then group 6, then 5, then 7, 8. So 1, 3, 2, 4, 6, 5, 7, 8. Not 1, 2, 3, 4, 5, 6, 7, 8. You're going to say, why is that the case? So there's a special stability with a filled subshell and a half-filled subshell. So let's say we're talking about the second row. Beryllium is 1s2, 2s2. Boron in the third group is 1s2, 2s2, 2p1. So beryllium's a little happier, so it takes a bit more energy to knock that electron out. Similarly, half-filled subshell. Nitrogen is a half-filled p subshell, right? It's 1s2, 2s2, 2p3, and then oxygen 1s2, 2s2, 2p4. So the nitrogen, you have to flip those two around. It's a bit happier. Now, some people rationalize this and they say, oh, the fourth electron in the oxygen repels the other ones. And you can tell all these stories, but you really got to go get to electron correlation energy and all this quantum stuff. That's grad school stuff. Maybe a few of you will get into that. Let me just define what we mean by ionization energy. Just write it out. Let's say I have sodium gas. It goes to sodium plus gas plus I1. So that's what we mean by the first ionization energy. And I do not put I1 on the right-hand side, do I? I1 would go on the left-hand side. You're putting energy into a system. And that's not even good. Let's write it like this. The first ionization energy, here's the best way. First ionization energy, then I write a colon. That is represented by the process where sodium gas becomes sodium plus gas and an electron is released. If I wanted the first ionization energy for magnesium, so I got magnesium gas, goes to magnesium plus gas plus an electron. So that's the first ionization energy for magnesium. If I want a higher ionization energy, the second ionization energy for magnesium corresponds to the energy needed to kick out an electron from an ion created. So you've already kicked out one electron. How much energy to kick out the next one? So Mg plus gas goes to Mg2 plus gas plus an electron. So that's the second ionization energy for magnesium. The third one, third ionization energy, you'd have magnesium 2 plus gas goes to magnesium 3 plus gas plus an electron. Okay, and the third ionization energy is greater than the second, is greater than the first. And if I had other ionization energies, they'd be greater still. The reason why they're greater is that you have one less electron. You have the same number of protons, but one less electron. So those protons, that effective nuclear charge, is getting larger because there's less electrons around. Another deal is there's a drastic increase in the ionization energy when a valence shell has been kicked out. So for example, for magnesium, you'd have a certain value for the first higher value for the second, and then a much higher value for the third, because the third ionization energy, you'll have already kicked out the first two electrons. So to kick out the third takes a lot more energy. There's a big gap there. For sodium, once you get the first ionization energy, you are now into the second shell. So the second ionization energy will be a lot more than the first. The third ionization energy would be more than the second, but the difference between the third and second is not as drastic as between the second and the first. Okay? Going down a group, we already said the atoms get bigger. The atoms get bigger, there's more screening, the ionization energy decreases. So the lowest ionization energy on the periodic table would be that of francium, which means francium is the most reactive. There's not much measurements on francium, but if you have them, francium is the most reactive, and it's going to lose an electron most readily. Readily means easily. Okay? So here, well, I already talked about this. Ionization energies just for magnesium, and you see the big jump from the second to third. Okay. Here we have, ooh, look at that, a nice 3D graph. Going down every group, well, hydrogen's in the first row, so it's special. But you see that the first ionization energy, second ionization, sorry, this is a plot of what? See, this isn't a good graph until I write this. We're talking here about the first ionization energy. So you see the first ionization energy decreases as you go down a group and increases as you go across a row. But it doesn't increase smoothly. You got the 1, 3, 2, 4, 6, 5, 7, 8, right? 1, 3, 2, 4, 6, 5, 7, 8. And that's a nicer drawing than what we have here. But you do see again, well, this diagram's not bad. You see those two kinks, those two so-called anomalies. Now it gets more complicated here when you're putting in the transition metals, but you see those being repeated, and so you can go this way, and you can to look across a row, and you can go this way to look down a group. Okay. Another periodic trend that we don't spend that much time on because the trends are not as strong is electron affinity. A neutral atom can add an electron to form an anion. The energy change when an electron is added to an atom is called the electron affinity. If I have an affinity for pepperoni pizza, that means I like pepperoni pizza. An atom has an electron affinity, that means it likes to get electrons. Nonmetals typically have larger electron affinities than metals do, because nonmetals want to gain electrons, metals want to lose electrons. So fluorine can be ionized to give you F plus an electron, or it can gobble up an electron and you can get the electron affinity. And energy is released when an electron is added to a fluorine atom to form fluoride. So a fluoride ion is more stable than a fluorine atom and a free electron. Okay. Some tables write it the other way around. So yeah, it's annoying. Sometimes you see the sign not written, but I'll try to be consistent. So the rough trend is electron affinity tends to become more negative from left to right across a row of the periodic table. So you see that fluorine is pretty high. Chlorine is even higher. Okay, so chlorine in fact has a higher electron affinity than fluorine. Fluorine has a higher electronegativity, which is more discussion in next chapter, but chlorine has a higher electron affinity. Okay, but again, you see there's no clear trend as you go into larger road periods in the periodic table, so we aren't going to make a big deal about electron affinity. But you have to know what it means and the rough idea about the trends. Okay. Here we're talking about the irregularities. We've already talked about that, so I'm not going to talk about it again. I'm going to repeat myself. Sizes of an ions. Okay, this is a discussion of ionic radii. This is on page 234. Okay, so cation is always smaller than the corresponding neutral atom. So I would have the size of lithium plus is smaller than the size of lithium. Because think of it, lithium is 1s2, 2s1, lithium plus just 1s2. So lithium is smaller than lithium plus. If you want to use the old school Bohr diagrams, you have 3 protons. I'll make that a little square. That's my nucleus for lithium plus. And then I got 2 electrons, and that's it. For lithium, I got 3 protons. I got 2 electrons. Then I got 1 more, right? So the lithium plus is smaller. So any cation is smaller than its corresponding neutral atom. Conversely, any atomic anion is always larger than the neutral atom. So if I got F minus, well, F minus is going to be bigger than fluorine. F minus, 9 protons trying to hold in 10 electrons. Fluorine, 9 protons trying to hold in 9 electrons. So the fluoride is got, it's larger because you aren't creating a new shell or anything like that. You have the same number of protons, but you got 1 more electron. The fluoride is larger because those 9 protons can't rein in the 10 electrons, as well as 9 protons could rein in 9 electrons. Okay, so that's our story with regards to sizes of ions. I could ask an interesting question like this. Let's say I got Mg2 plus and Na plus. What would be smaller? So it'd be Mg2 plus because it's 12 protons acting on 10 electrons. 12 protons, 10 electrons. Whereas Na plus is 11 protons and 10 electrons. So these are both isoelectronic, and that would be greater than neon, which would be 10 protons and 10 electrons. Not greater, sorry, smaller, more compact. And fluoride would be bigger, and then oxide, nitride, etc. So you can arrange those isoelectronic series in order of increasing size or decreasing size. This diagram I found rather confusing. I don't like it. But it does show you what we just talked about, that the anions are larger than the corresponding neutral atoms and the cations are smaller. Okay. Here we see trends in a isoelectronic sequence. We see the atoms get smaller as you go across. Neon, you would just have to guess for it. And you see the ionization energies get larger as you go across. Okay. So there's some practice problems for you to try on sorting the ionic radii, atomic radii, electron affinity, and first ionization energy. Remember, there's no trends for second ionization energies or higher ionization energies than that either, because you start losing shells, so it's not proper to get a trend associated with that. Okay, let's go to the slides for a second, see if there's anything to add there. We did that one. We looked at the trend there. Ionization energy, electron affinity, essentially no trend. Ionic radii, we looked at that. Okay. So now we're going to look at some energetics of ionic compounds. Okay, and this is in our textbook on page 236. And so let's take a look at this here. This, I think, is going to be new for all of us. We don't look at all the details about it, but at least a little bit. And this is the last topic in the chapter, actually. So this is a shorter chapter, and that's okay. Here we have sodium chloride, which we're going to revisit. And you have a lattice, so it's a repeating set of cations and anions. Na plus is small, chloride is bigger. So sodium chloride contains Na plus cations and chloride anions, and they're organized in a three-dimensional cubic array. And soft, lustrous sodium metal reacts vigorously with yellow-green chlorine gas to form sodium chloride. We know that as table salt. It contains sodium and chlorine in a 1-to-1 ratio. So yeah, sodium cation, chloride anion. Carbon monoxide is also one atom of carbon, one atom of oxygen, but it doesn't form an ionic compound. So how do we get these energies associated with formation ionic compound? You have stabilization through the ionic attraction, and we're going to break it down into the forces to put it together. And it becomes what's called a Born-Haber cycle is one way they talk it. It's not the Haber process, but it's also a thing known as lattice energy. So we're going to add up some energies. Okay, so how can we make it happen? First, let's say we take a sodium atom, solid, and we pour energy in to make it a gas. So that will be called the sublimation energy. Then we take a chlorine gas molecule and we chop it to form chlorine gas. Okay? They put a half in front of there. I wonder why they put the half in front of there. Sublimation energy, is that even balanced? That's not a balanced equation, is it? Okay, let's put a little question mark there and go to the next one. We have, oh, because we're going to need the layer, fine, right? Yeah, okay, it's 2 times, it's the bond energy for one chlorine bond, right? And we want the whole thing. What we want to look at is how much energy is released or absorbed when we form 1 mole of solid sodium chloride from its constituent elements in their standard states. That's really a heat of formation, isn't it? Sodium solid and half Cl2 gas. So the sodium gas, we can zap it and make it Na plus gas. The chlorine gas can gobble up an electron, and that's the electron affinity. And then we talk about the condensation of the gas phase ions to form NaCl solid. So those 5 processes, add them together. Is it all going to work out? Let's see. Na gas cancels. What else cancels here? Na plus gas cancels. We got a Cl gas. Oh, let's see. What else do we got here? Na solid there. Cl minus cancels. So Na solid, I got a half Cl2 gas. So a chlorine gas is going to cancel. You know what? This should just say Cl. That's what it should say. I knew there was something bugging me. It should just say Cl. So that Cl goes away. And ionization energy, an electron is released, so that goes away. So the book was sloppy. Sometimes it's sloppy, but I fixed it, so thank you very much. Okay, you are welcome. So now we end up with Na solid plus half Cl2 gas goes to NaCl. So the net energy change for the reaction is the sum of the energy changes of the individual atoms. Okay, so step 1 was sublimation, and it turns out that it was 105. Okay, ionization is 495, bond dissociation is 120, electron attachment, which is electron affinity, is negative 348.5, and condensation, we can use the Coulomb's law. We won't go into the details there. It just turns out to be minus 769. Okay, so that was condensation. Let's go up and look at this chart again. Bond dissociation, electron attachment, condensations. And then in the condensation step, so we're releasing energy, Coulomb's law, you have a constant, then you have the charge on each ion divided by the distance between them. The energy released turns out to be minus 444 kilojoules. That is the only part of the energy released in forming the crystal. Okay, and then if you add up the other participating interactions, attractive and repulsive, it turns out to be minus 769 kilojoules per mole. So that is also referred to as the absolute value of the lattice energy. Okay, so the lattice energy turns out to be positive 769. Okay, lattice energy is how much energy is needed to break a solid into the constituents gaseous, cation, and anion. So now that number would be given. The lattice energy in this question, you add everything together and you get minus 397 kilojoules per mole. The calculated energy is within 5% of the experimental value, so that's not bad. Okay, so a thing snuck into this question, this series of steps, was this new concept of lattice energy. So lattice energy is the energy required to separate an ionic compound into its ions. And here is a good picture, actually, showing what's going on. So here you got sodium, and it sublimes, so from solid to gas, and then we take half the bond energy of Cl2 to get Cl. So those are both positive, right? This is positive, this is positive. We ionize the sodium to make Na+, so that's positive. Then we want to make Cl-, so that's electron affinity, that's release of energy. Then we want to make the lattice energy, which is energy release, so 769 going down. And so then you're going to take the difference between your input and your output, and that's this value right here. So that is the heat of formation of sodium chloride. I noticed they aren't using, oh no, they did. I was just going to say they aren't using the Born-Haber cycle title, but yes, they are. They just was in the key concept. An energy cycle like the one we just looked at is called the Born-Haber cycle. Okay. Example 5.9 is for 2 electrons, electron affinity twice. That's, you can look at that one on your own. But typically, if you'll find something like this, we'll just look at one. It's not energetically favorable to have Na2+ and Cl2-. Okay. The rest of it, trends in lattice energies. Yeah, we can talk a little bit about that. This is actually interesting. Think of lattice energies, how strong a crystal lattice is. The stronger it is, the more energy needed to break it apart. And what we're saying is that the lattice energy, or I'll just say the absolute value of the lattice energy, so we have to argue about positive or negative, it increases as Q increases and R decreases. So the greater the charges, the net charges on the cation and or anion, the greater the strength of the ionic crystal. The closer the cation and anion are to each other, the greater the strength of the crystal. Okay, so if I had something like MgO versus, that's magnesium oxide, versus NaF, well, magnesium cation, so it is magnesium 2 plus, O2 minus, Na plus, F minus. Magnesium oxide would have a higher boiling point, a higher melting point, because magnesium 2 plus is smaller ionic radii than Na plus, and O2 minus, well, that is a little larger than F minus, fine. So those are around this, so that's not a huge difference. But magnesium and oxygen are both 2 plus and 2 minus. Sodium plus and F minus are just 1 plus and 1 minus. So magnesium oxide is going to have a higher lattice energy than sodium fluoride. Okay, so some trends here. Lattice energy of alkali metal chlorides decreases as the size of the cation increases. Right, so NaF, NaCl, NaBr. So NaBr would be a smaller lattice energy than NaCl because bromide is bigger than chloride. So you see how we're using the idea of ionic radii that we just learned earlier in today's lecture to help us understand the trends in lattice energy. Okay, let's see what else we have here. Trends in lattice energy, so that's good. So yeah, you see it. Lithium fluoride is 1,030, then it goes down, down, down. Okay, now when you start putting an oxide, well, that's a different story, right? Because now you're looking at a different empirical formula, and you also have a charge of 2 minus. So that's a different ball of wax. Okay. Section 5.6 is really one that you can read on your own. It's not one that we really ask specific questions about. Same with this descriptive stuff about the S block elements. We don't really concern ourselves with that too much. You can read it for your own enjoyment. The P block elements, examples of them. And then we get to the end of the chapter here. I told you it would be a shorter one. So we start with orbital energies, the screening effect, and then we remind ourselves the structure of the periodic table, core electrons versus valence electrons, and then we look at electron configurations, Hund's rule, and then we got into the trends, the periodicity, and atomic radii, ionization energy, electron affinity, Born-Haber cycle, lattice energies, and then we get into the learning exercises. That's for you to do. Let's just see if there's some stuff in the slides that are helpful. Okay, well, we went through this one. Okay, lattice energy, and then no, nothing more to help with the slides. Okay, so that's chapter 5, and there'll be end of chapter questions and assignments and all sorts of fun stuff to do related to this. Have fun.